All right, this lesson is going to be about vector-valued functions. We've talked about vectors a few times in the past when we talked about velocity and acceleration. The velocity and acceleration are vectors because not only do we talk about the speed, let's just say, at which we're going, but also the direction. So velocity is magnitude or length, speed, and direction. Are we going forward? Are we going backward while we're going that speed? So we're going to explore those a little bit more and look at them in a more formal way. So there are three different ways you can write a vector. The component form is the form that you're going to see the most often. So when we denote the fact that we're talking about a vector, we use a bold variable. So in our case, our bold variable is r. This is vector r. And writing it in component form is how we've been writing parametric equations and polar equations, where we look at the x component and the y component separately, and how those components are determined based off of a parameter. And in this case, t is the parameter. So how is x changing as time is changing? How is y changing as time is changing? So the big thing to note is those pointy brackets around the parameters, around the components, I mean. Unit vector form, you're not going to see that much, if any, on the AP exam. That's more something you're going to see in a college level vector calculus course. But the unit vector form is saying, let's take x of t and multiply it by this horizontal unit vector called I. And it's horizontal, I meaning it's 1 unit in length, so that is the unit vector I. It's horizontal, 1 unit in length, and then take that in x of t, so that will change where we end up. Not something you should really worry too much about. And then the vertical unit vector is the vector j. And then parametric form is just looking at its two components as a parameter, like with parameters, x of t, y of t, like that. That's parametric form. Most of the time you'll see this in component form. Okay, let's graph one of these. We're going to graph one just like we would graph a polar equation, just like we would graph any parametric equation. We're going to graph 3t squared, t plus 4. So notice this is in component form. We're going to look at these two different components. We will graph t, use t to graph x and y. So I'm just going to graph a few points. I'm going to start with t equaling -3. -3 squared is 9 times 3. That's x coordinate is 27, and -3 plus 4 is 1. So y is 1. Then I'll plug in -2 squared. That's 4 times 3 is 12. -2 plus 4 is 2. And then if I plug in -1, -1 squared is 1 times 3 is 3. -1 plus 4 is 3. And we keep going from there. Let's see. So then 0 squared times 3 is 0, plus 4 is 4. 0, then 1 squared is 1 times 3 is 3. 1 plus 4 is 5. 2 squared is 4 times 3 is 12. And 2 plus 4 is 6. And let's just go one more just to balance this out a little bit. Let's go with t equal 3 squared 9 times 3 is 27. You can notice the x values kind of looking symmetric. The y value is not quite as much. 3 plus 4 is 7. So let's see if we can graph this out, see what it looks like. All right, so the x values are pretty large. The y values, not quite so much. But let's just see if we can create an x and a y axis here. And we'll leave enough room for the y values to go up to 7. And we're going all the way up to 27, so let's count by 3s. 3, 6, 9. And on the y-axis, 1, 2, 3, 4, 5, 6, 7. Okay, so we'll plot the first point, 27, 1. So that's here. And then the next point is 12, 2. The next point is 3, 3. The next point is 0, 4. The next point is 3, 5. The next point is 12, 6. And the final point that I've graphed is 12, 7. So this is a parabola that is opening on its side. And we can talk about direction. This was graphed out in that direction, just like we've done with every other parametric equation. That's the orientation of that graph. Okay, so that's just, vectors are just parametric equations. Let's start doing a little bit of calculus just to see how this is going to play out for the calculus portion of our show. Let's look at limits. I'm going to change colors. Let's look at the limits of a vector. They're nothing too crazy here. So when we talk about limits, if we have a vector r of t that has x and y components, then we can find the limit of this vector. So the limit as t approaches some a value for r of t looks like this. It's the limit of each component separately. So it's the limit of x of t and the limit of y of t, which probably would have been intuitive, but it's good to see it written formally. So if we look at an example, I'll go to the next page. So I want you to try this one then based off of what we just talked about. Try this example. I would like you to find the limit the limit as t approaches 0 of our components, our vector e to the negative t sine t over 2t. Please stop the video. Go give that a try. Okay, welcome back. I'm going to find the limit of each component separately. So the limit as t approaches 0 of e to the negative t. I can think about this as, since that's e to the negative t, I can think about this as e to the t power like this. Let's see, as t approaches 0, we end up with, sorry, I just lost track for a second. As t approaches 0, if we replace t with 0, that makes this e to the 0 power. E to the 0 power is just 1, so this limit is 1 over 1, or just 1. Okay, e to the 0 power is 1. Anything to the 0 power is 1. 1 over 1, we get 1. Now let's look at the second part. The limit as t approaches 0, sine t over 2t. If I replace t with 0, I get the sine of 0 in the numerator, which is 0, and 2 times 0 is 0. L'Hopital's rule. So using L'Hopital's rule, if I find the derivative of the numerator, oh, I did that wrong. Don't do as I do. The way we should do this to be very clear, oops, I thought I deleted it. The way we should be doing this, shame on me, is looking at each limit separately. The limit as t approaches 0 of sine t equals 0. The limit as t approaches 0 of 2t is also 0. So L'Hopital's rule. I am a bad influence. Look at those limits separately, not together. So using L'Hopital's rule, then I will find the derivative of the numerator, which is cosine t. I will find the derivative of the denominator, which is 2. If I plug 0 in now, the cosine of 0 is 1, and we have 2 in the denominator. So finally, the limit of this vector valued function, the limit is this. It is 1, 1/2. Okay, that's the first part of our calculus exploration. Let's talk about the derivative, and then we'll use the derivative to do some things. So let's look at some derivatives first. New color, let's go with orange this time. So differentiation now. Okay, let's look at differentiation. I'm going to make my pen just a little bit thicker. If we have a position vector, we'll call it r of t just because we're on a roll with that. And if that position vector is x of t, y of t, then the velocity is the derivative of that position vector. So the velocity vector, v of t, is the derivative of r of t. And that's just x prime of t, y prime of t. Now if we look at the acceleration vector, this you could probably figure out where this is going to go. Acceleration vector, a of t, is the second derivative of r. So that's the second derivative of the x component, the second derivative of the y component. Let's do an example of this, and then we'll start using all of this information in some applications. So let's find the tangent vector. Find the tangent vector to the curve. Let's use a different variable other than r. Let's call it m of t. How about n of t so I don't have to write it too much? N of t, there's our position. Here's the position curve, 3t minus 1 squared, and the cosine of 2t. At t equals pi over 6. Okay, I'd like you to go try this. Go try to write a tangent vector for this curve at t equals pi over 6. Okay, welcome back. I hope you actually tried it. So first thing I'm going to do is find the derivative of n of t. So I'm going to find the velocity vector. The derivative of 3t minus 1, we're going to use the chain rule. So that's 2 times 3t minus 1 to the first, multiplied by the derivative of the inner, so that's 3. For cosine, I will also find the derivative. So the derivative of cosine is negative sine. So it's the negative sine 2t multiplied by the derivative of the inner function, that's 2. So here's just the velocity vector. This is 6 times 3t minus 1 and negative 2 sine 2t. But the question said find the velocity vector at t equals pi over 6. So I'm going to replace t with pi over 6 to find the velocity vector that we were looking for. So that's 6 times 3 times pi over 6 minus 1, and then negative 2 times the sine of 2 times pi over 6. Okay, we're going to simplify this. 3 times pi over 6 is pi over 2. 6 times pi over 3, 6 times pi over 2, is 3 pi. So 3 times pi over 6 is pi over 2. And if I multiply 6 through to that, 6 times pi over 2 is 3 pi, minus 6 times 1, so minus 6. So there's our first part of the velocity vector. And then 2 times pi over 6 is pi over 3. The sine of pi over 3 is the square root of 3 over 2. Square root of 3 over 2 times negative 2 is the negative square root of 3. This is our velocity vector at t equal pi over 6. Okay, I think that's enough for now. I'm going to stop the video, and in the next video we will start using some of the derivatives and things we know about these vectors to solve some problems like FRQ